Okay. Next, we are coming to the Euler's angle method, which is another method of configuring the orientation of the wrist. RPY is the one that we saw just now. And now we are going to look at the Euler's angle configuration method. Here, again, we are assuming that, N, O, A are parallel to the X, Y, Z at some particular position of P. So some particular position is there, and there we are having a frame NOA. Now the Euler's angle basically again has three, but it's slightly different. The difference is that the first motion that we decide, the first motion that we decide is, let me take, okay. The first motion that we decide is with respect to A, we have an angle change of phi. So let me draw that. So if with respect to A, I am going to turn in anti-clockwise direction, then N will come here. So there is an angular change of phi here. Let me draw that more clearly. There is an angular change of phi. Similarly, O also undergoes an angular change of phi, and it is right now here. A angle does not change. Okay, so this rotation is basically, let me call it as rotation with respect to A at an angle of phi. Okay, next this is followed by the second rotation, which will be with respect to O axis. Now where is the O axis? The O axis is currently here, isn't it? So let me draw that. So by drawing it, the O axis is here, the A axis is still parallel to Z, okay, and the N is somewhere around here. Let me draw it a little bit more flat. Okay, the N is somewhere around here. This is O, this is A. Yeah. Now with respect to O, I am going to make a rotation, and that is again, so with respect to O, if I am going to look, then with respect to O, anti-clockwise means I have to move in this direction. So if I move in this direction, the axis will move here. So this is where A is going to be, and similarly this is where N is going to be. So this angular movement, let me name this as theta. Theta. It's not coming correctly. Let me draw it outside. So this is theta. Okay. The same angle theta will come here. So A and N, both of them have moved by an angle of theta in anti-clockwise direction with respect to O. So that is the second rotation. So rotation with respect to O axis of theta angle. The third one is not with respect to N. It is again with respect to A. So right now I will draw where the A is. So right now the A is oriented like this. O is oriented like this. This is where my A is. It's not parallel to Z. And then my N is currently oriented in this direction. So let me draw that properly. N. And now again with respect to A, I am going to have the third movement, the third rotation. Sorry, I will use a different ink. So yeah. So I am having again moving in anti-clockwise direction. My N axis will move this much. That angle, let me call that angle as, let me call that angle as psi, and similarly O will also move that much angle, and that's how my orientation is going to be. So it will be basically rotation with respect to A axis of an angle of psi, and that is the three. So let me write the sequence. The sequence is going to be rotation of A with respect to angle phi, rotation of O axis with respect to, or rotation of O axis for an angle of theta, and rotation with respect to A axis for an angle of psi. So these are the three rotations, and with any value of phi, theta, psi, you can achieve any orientation of the wrist. Okay, so let me write the equation for that. The equation for that, as we know, this is all based on A and O, which are the frame and not the fixed frame. So it's all going to be post multiplication. So I will be able to write Euler for phi, theta, psi is going to be post multiplication. So rotation of A for phi angle, rotation of O for theta angle, multiplied with rotation of again A for psi angle, and together that will give me a result for the matrix, the 4 by 4 matrix, which I can write as, first column we have cos phi, cos theta, cos psi minus sin phi, sin psi, like that. Second column, third column, fourth column. Again, in the fourth column you can see that there is no position. All the position is written as 0, 0, 0, because we are only talking about the orientation change. Okay, now see this equation and this equation. Okay, you can use any one to actually find out whichever is the, wherever you want to orient the tool to. You can use any of these two configuration, either Euler's angle, or you can use the RPY angles. Now, one of the things that we should note here, that we should not forget, is that, let me write that, note, okay, note, we have assumed initially that NOA is parallel to reference axis XYZ. That we have always considered. If you remember, or if you look here, we have started always with the first movement. Before that it was NOA parallel to XYZ. Even in Euler's angle case, okay, or even in RPY, in every case it was parallel. That is what we assume. Okay, even if it is not parallel, okay, even if it is not parallel, we can find out what will be the final orientation after RPY movement by multiplying, which multiplication? Post multiplying with the previous orientation. So suppose if the initial orientation was not parallel, it was something else. That means if it is parallel, then we will have an identity matrix, isn't it? In the orientation side, 3 by 3 matrix will be an identity matrix. So initially, if it is not oriented, if it is oriented parallelly, then it will be an identity matrix. So 0, 1, 0, 0, 0, 1. Whatever be the value in this, here, whatever be the values, we are mostly interested in the orientation. The orientation part will always have identity matrix to show that it is parallel to X, Y, and Z. Now, if this orientation is not this, if this orientation is something else, if the value is something else here, then all you have to do is you have to post multiply that matrix, whatever is the current matrix, that with that you have to post multiply the Euler one or the RP one to find out what will be the final one. So let me write that as a point. Okay. So we have assumed initially that we have assumed initially that NOA is parallel to XYZ, but if it is not parallel, then the final orientation of the wrist or the hand will be a combination of the previous orientation post multiplied with the RPY or the Euler matrix that we have got just now here. Another thing that we should also note is that now we have done for all the 6 joints. The first 3 joints will give us what is the position of the wrist, and the last 3 joints will give us the position of the the orientation of the wrist. And together, what will be the kinematic equation? So I can write that the final kinematic equation which shows the position and orientation of a 6 degree of freedom robotic arm will be a multiplication of the robot first 3 joints, it might be a cylindrical robot or a spherical robot, followed by the Euler's one or the RPY one. Okay, so let me write that as a point. So the final position and orientation of the tool in a 6 degree of freedom robot arm will be a combination of the position matrix as well as the orientation matrix that we have studied in section 3.42 and 3.43. So I will write as an example. If we have a spherical motor, not spherical motor, spherical arm. So if we have a spherical positioner and a Euler's wrist, okay, then our combined with the combined position or the transformation matrix of R with respect to the universal U will be given by the multiplication of the spherical positioner, which is, if you remember, we have written T spherical with R theta phi, which you have already seen how it is written, multiplied with the Euler one, which is having phi theta psi. So we have to multiply both these matrices that we have already studied. Remember here, this theta and phi that we have written for spherical and the theta and phi we have written for the Euler is totally different. Okay, thank you.